Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Comparison Tests for Improper Integrals. As always, please be an attentive learner while watching this video. By way of introduction, often we are not concerned with the actual value of these integrals. Instead, sometimes we might only be interested in whether the integral is convergent or divergent. You want to pay attention to the question that's being asked and the problem you're trying to solve. Also, there will be some integrals that we simply won't be able to integrate, and yet we would still like to know if they converge or diverge. So to deal with this, we have a test for convergence or divergence that we can use to help answer questions of convergence for an improper integral. Now, and this comparison test foreshadows a similar test that we will use in our study of infinite series, so I'm going to say it is doubly important. Now, this test is only being discussed here for the subcase of an infinite interval integral. However, versions of this test do exist for other subcases of infinite infinite interval integrals, as well as can be used for integrals with discontinuous integrands, and the students should think about that as they reflect on these. So here is a statement of the comparison test. So if f of x is bigger than or equal to g of x is bigger than or equal to 0. So both must be positive, and in our case here, f is the largest one on the interval from a to infinity. And this a could be any number, no matter how big. Then there are two conditions. If the improper integral from a to infinity of f of x dx converges, then so does the integral, improper integral from a to infinity of g of x dx. So if the top one converges, that means the lower one converges. And similarly, if the integral from a to infinity of g of x dx diverges, then so does the integral from a to infinity of f of x dx. So you see, if this one blows up, so does this one. If this one converges, so does this one. And a student should realize that no matter how large the lower limit is, this theorem is true. So you see, the convergence or divergence depends only on the end behavior of the function. Sometimes when I teach in class, I talk about it's all about the tail of the function. And sometimes it's useful to think about area. If f of x is larger than g of x, then the area under here must also be larger than the area under here. And similarly, if it goes the other way, you can conclude the second piece. So thinking about area hurts. Now, it will really probably surprise you, but I will tell you from my experience, students often misunderstand and misuse this test. If the smaller function converges, there's no reason to believe that the larger will also converge. After all, infinity is larger than a finite number. And the larger function diverges, there's no reason to believe that the smaller function will also diverge. You might think, how could anybody do that? I see it all the time in the heat of an assessment. So be careful to keep this well in mind. Here's a problem for you to do then, using that test. Determine if the following integral is convergent or divergent. And this is the integral from 2 to infinity. This is cosine squared. That exponent is a 2x divided by x squared dx. I guess all the numbers in this problem except for infinity are 2's. So anyway, you know what to do. Let's see how you did. Okay, here's the statement of the problem. Now, one thing you should know is that cosine squared of x is always between 0 and 1, always. And so we're going to compare it against this integral, which goes from 2 to infinity, 1 over x squared dx. Now we had a theorem about this, and we know that this does converge. And so that means that since the cosine squared of x over x squared is less than or equal to this, then our original integral is less than this. And so by the comparison test, we know that this integral, the problem, also converges. I am asking you not just to guess or speculate about convergence or divergence, but actually explain to me in words why it is true. And the essay part counts a lot more than a guessing part. Here's another problem for you. Determine if the following integral is convergent or divergent. Now this is the definite integral from, it's not a definite integral, it's an improper integral from 3 to infinity 1 over x plus e to the x dx. You know what to do. Let's see how you did. Let's start here then. Now, 1 over x plus e to the x. Now, e to the x is positive, so 1 plus e to the x is less than 1 over x. But you see, this is bigger, certainly, but this integral diverges. That's not what the problem is asking. It has to go the other way, because the dominant function, the bigger function diverging, doesn't tell you anything one way or another about the smaller function. So if you went this way, you guessed wrong. Let's try it again. And this time we're going to say that, well, x is positive over this interval from 3 to infinity. And so that means that 1 over x plus e to the x is less than 1 over e to the x, and that's e to the minus x. Now we know that e to the minus x converges, like here's the calculation, this improper integral would be this limit. We find the antiderivatives and subtract them, and we get that this is e to the minus 3. So that converges. So this means that this integral then is convergent. I mean, we just showed that. So by the comparison test, since this is smaller, this also converges. You see, you got to be careful which way you go. Here's another example. Determine if the following integral is convergent or divergent. This goes from 3 to infinity. This is 1 over x minus e to the minus x dx. You know what to do. Let's see how you did. All right, now here, 1 over e to the x is, excuse me, 1 over e to the x is positive. So we're subtracting something positive from the value of x. So we're making the denominator smaller. That makes the fraction bigger. So 1 over x minus e to the minus x is bigger than 1 over x. But we know that this smaller one diverges, and so from the p-test in improper integrals. So by the comparison test, we know that this also must diverge. Another example. Determine if the following integral is convergent or divergent. This is the integral from 1 to infinity. This is 1 plus 3 sine to the fourth of 2x divided by the square root of x dx. You know what to do. Let's see how you did. All right, so here we know that 1 plus 3 sine to the fourth of 2x, this 3, sine to the fourth, since I'm raising that to the fourth power, this has to be a positive number. So 1 plus a positive number is bigger than 1. And I'm leaving the bottom alone. So this is 1 plus this is bigger than 1 over the square root of x. But we know that the smaller one, the square root of x, diverges from the p integral test. And so by the comparison test, this integral also diverges. Let's do another example. Now, up to this point, all the examples that we used manipulated either the numerator or the denominator to use the test, but actually sometimes you have to manipulate both. Perhaps a harder problem. Let's do an example where we will see this. Determine if the following integral is convergent or divergent. So this is the definite integral from 2 to infinity. This is 1 plus cosine squared x divided by the square root of x times 2 minus sine to the fourth x dx. You know what to do. Let's see how you did. Now, 1 plus cosine squared is 1 plus a positive number. And so that's going to be bigger than if you replace it by 1. So you know that this integrand is bigger than this. And we also know that sine to the fourth is between 0 and 1. So that's a positive term. So that means that what we get here is that the denominator and the numerator, here we already had this one, but what we're doing is we're taking the square root of x and we're multiplying it by a positive number. And so if I go to a positive number that is, if I make this this number as large as it can be, then that makes this, I'm making the denominator bigger. And so that means that I have the inequality going this way. So you see this is bigger than 1 by the first discussion over 2 the square root of x. But this diverges. The 2 in the denominator really doesn't matter because I just pull it out, but this is 1 over, and this is x to the minus 1/2. And so the 2 in the denominator does not affect that. So this integral does diverge. The smaller one diverges. So by the comparison, the upper one also diverges. Another example. Determine if the following integral is convergent or divergent. This is the integral from 1 to infinity of e to the minus x over x dx. You know what to do. Let's see how you did. Now, normally the presence of an x in the denominator would lead us to guess perhaps divergent. However, the exponential in the numerator will approach 0 very fast, and actually you could think about that as being e to the x in the denominator. So let's look at this. Here, what we're doing is we have e to the minus x over x. And you see x is bigger than 1, so when I put x in the denominator, it makes the inequality go this way. So the integrand e to the minus x for x bigger than 1 is less than e to the minus x over x, which is just e to the minus x. Now, we have already shown, I think we've computed this more than once, that this integral, which is the bigger one, converges. And in fact, we've done that for a lower limit of 3, and changing that to 1 won't change the convergence. Therefore, by the comparison test, this integral also converges. Again, in the problem, I will expect you to tell me convergent or divergence and also write me a coherent essay about why that is true. Another problem. Determine if the following integral is convergent or divergent. Notice that there's no numerators or denominators here. It's just the integral from 1 to infinity. This is e to the minus x squared dx. You know what to do. Let's see how you did. Well, this function goes down as x getting bigger. So if x1 is bigger than x2, then e to the minus x1 is less than e to the minus x2. In other words, plug in a larger number and the function gets smaller. Now, from the limits of integration, we know that x is bigger than 1. And that means if we square x, it gets larger because it's bigger than 1. 2 squared is bigger than 2. 3 squared is bigger than 3, so forth. 1.5 squared is bigger than 1.5. So that means that x squared is bigger than x, provided x is greater than 1. Now, we can only say this because x is bigger than 1, because if x is less than 1, x squared is less. But we're using that fact because we do have that it's bigger than 1. So that means that x squared is bigger than x. I'm going to apply that to this. So e to the minus x squared is less than e to the minus x. So e to the minus x is the larger function than e to the minus x squared, but we know that this converges because we've done that calculation before, and so by the comparison test we know that this integral is convergent. Another example, determine if the following integral is convergent or divergent. Now here we're going from 1/2 to infinity e to the minus x squared dx. You know what to do. Let's see how you did. Now, we used heavily in the last theorem, the last example, that x was bigger than 1, and we saw that this e to the minus x squared was the red function and it's less than the blue function. So we could determine that what happens here is that this part of the integral converges. But we have something else going on. Whenever we're less than 1, e to the minus x squared, the red curve is bigger than the blue curve. But we can't compute this directly. But we can conclude by using approximate integration, numerical integration, we can come up with a value for this, so it is finite, adding it to something that also is finite. And so this integral, this, is the sum of those two integrals. And so the combined integral will converge because both converge. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're in this together. May God bless you all.